Well, thank you very much for coming to these lectures. We're very privileged to have Professor Pierre Deligne from the Institute for Advanced Studies, who will give 6 lectures, 2 today, 2 Monday of next week, and then the last 2 lectures on Friday of next week. And the topic will be multiple zeta values.
So first I recall the definition. Okay, so for this sequence of integer S1 up to Sd, when we have this, we say we are in depth d and weight the sum of the Si. One define this expression, and I like to call this an iterated sum of the function 1 over n S1, 1 over n Sd, the reason being as follows. If you start from here, you have this function 1 over n Sd, you can sum from 1 up to k. Up to k minus 1. Now, this is the function of k. You consider this function times the 1 over n Sd minus 1 function, and you repeat the process. So for 2, I am just telling that summing over n1 bigger than n2, yes, at a vertical or horizontal one. I hope I have it right, one make something like that. But it will be useful to compare later with iterated integral, this notation. Now, yes, what the Si I want to take Si to be integer at least equal to 1, and S1 at least equal to 2 to have convergence. Convergence is easy to see. Suppose you have this sum. You first sum over n1, so you have to sum 1 over n S1 for n bigger or equal than the next number, n2, and this sum, first it diverges in S1 is 1, and also when S1 is bigger, you can approximate it by the integral from n2 to infinity instead of taking the sum. And so you get something which is of order of magnitude 1 over S2, S1 minus 1. And so you see that as far as convergence is concerned, you can drop the first and replace S2 by S1 plus S2 minus 1, and so on. So this is really the condition for convergence. Also, that's one way to think how to proceed if you want to evaluate numerically this sum. Instead of this first rough approximation, when you sum over n1, you go only after a few terms and you replace by what is given by Euler-Maclaurin summation formula, a few terms, and then it's relative. Especially if this S1 is big, this is quite fast. Now, such sums were first considered by Euler. First, of course, for d equals 1, when one gets Riemann zeta function. And Euler did a lot for it. So, for instance, he proved that zeta of 2n is of the form pi at some power times some rational number, which he found explicitly. But he also did much more. He computed zeta of 1 minus 2n. He checked the functional equation between 2n and 1 minus 2n. He guessed the functional equation in general. And he even checked it, as I remember. First, he checked that it was, and he checked, I don't remember where, but some other point, he checked the functional equation also. Now, you may wonder what this means, computing at 1 minus, maybe I would say 2s, where s is an integer, where you have a sum of positive power of n, which you have to take. So the point of view of Euler was somewhat like the point of view of modern physicists, that a formula has a meaning. You don't have to ask yourself what is the meaning of it, but it's interesting to compute the value. So for him it was clear this summation of positive power had a meaning, and then one had to compute and to possibly check nice identities. And his main tool for computing was the Euler-Maclaurin summation formula, which is now also, if one wants, a way to get the analytic continuation of Riemann zeta. Yes, so that's the case d equals 1. Now, d equals 2, I think it was a question of Goldbach which made Euler looked at it, but I also would think that it was a try for him to understand the value of zeta function at odd integer. For instance, one of the first things he proved is the following beautiful identity. Sorry. Which was quite a number of proofs, and the proof of Euler was quite nice. So one may think that he was hoping that by embedding the set of all zeta value in this bigger set of deep zeta value, when one had a number of non-obvious identities, one could get something about the value of zeta at odd integer. Of course, he did not reach anything like that, and our present understanding is that one can tell nothing about number like zeta of 3. They are completely new quantity for each odd integer. But he found some very nice systems of mysterious identity between d zetas and between zeta and d zeta value. I don't think he looked at I or D, but his methods were applicable also for I or D also. Yes, now I would like to make some comment about a little bit already about the nature of those quantity. So here I have taken strict inequality sign all the time in defining the sum. Euler was rather using bigger or equal sign, so the number he was considering were slightly different. For instance, in the sense of Euler, the S1, S2 you would have considered, he was not only summing when you had strict inequality between n1 and n2, but also additional term where they were equal, which was just giving an additional zeta of S1 plus S2, sum over n of ns1 times ns2. And there are some reason to prefer the choice we make now, but not really extremely compelling reason. So this thought that there is some zeta function, you would not dream to tamper with it, to make a little change, to add one or to do anything like that. You would destroy Euler product expansion and so on. For higher d zeta, you have some choice. It's not completely clear what is the best way of labeling them. What really makes sense is the Q-linear combination of multi-zetas with some characteristic. For instance, one class which is relatively reasonable is to fix the weight, the sum of the SI, and to take d smaller or equal to some number. This is some vector space which is reasonable, which you don't want to temper it. But the exact, and you see that if you use Euler definition or present definition, you don't change those linear combination of multi-zeta with bounded depth and fixed weight. Then there are also some so this is a warning not to take the exact number too seriously. Now there are some generalizations which are interesting. One of them is what I would call L S1 SD Z1 ZD. So it's given by the same sum over the same d tuple of integer, same denominator, but in numerator you put z1 n1 up to zd and d. So at first side it's a function of d complex variables, which at least is convergent well when all zi are absolute value at most strictly smaller than 1. And if you are on the boundary, usually it will converge too. So those are interesting functions. They satisfy system of differential equation, which show that they are have continuation on the wall of Cn. They are given by some iterated integrals also, but what will especially interest me is special value of those functions when you fix n and you take zi to be nth root of unity. So, for instance, if I take simply n equals 1. Sorry, n equals 1 is the previous case, just z equals 1. For z equals 2, it means that you put some signs in a numerator, the sign which is the parity of the sum of the ni. You have depending the ni for which you put zi equals -1. Still for n equals 2, one comment I want to make is that if you consider just the case of d equals 1, then in that case you gain very little by allowing yourself such things, because on the one hand you have summation 1 over ns, and on the other hand, you have summation -1 at the power n and s. Now, for s equals 1, you get something new. This is, here you are at the pole, you don't take it. Here, you recognize the expansion of -log2, so we have one more number which came up. But for s bigger than 1, you have nothing new. Let me call this zeta minus with this sign. Then going from here to here is just changing the Euler factor at 2. What you have is that you look at zeta if you add to it zeta minus, the n which are odd cancel, because you have plus 1 or n minus 1, and you are left with twice the sum for n even. Now if you look at the sum 1 over ns for n even, and you compare term by term with the usual zeta, you get 1 over 2s times ordinary zeta. And from this, you see that zeta minus, you can compute it from zeta. So that's the case d equals 1. For d bigger than 1, the story is different. You cannot use in general such a trick. The only thing you let it be d zeta. So you can consider plus plus, plus minus, minus plus, or plus plus for given S1 and S2. Now if you take the sum of the 4 cases, then you again destroy all the odd n, and you reduce the sum of those 4 to, by the same trick, to an ordinary d zeta. But it only tells you that the sum of, sorry, here it should be minus minus, only tell you that the sum of 4 things you recover something like the first one, but still you have more which is left. And indeed, one has, with signs, one has many more d zeta or multi-zeta than ordinary multi-zeta. And also I was taking an extreme case of n equals 2 here. When n is bigger, you really get more even for d equals 1, because you get all Dirichlet function for this n by taking linear combination. But for n equals 2, there is no character of z mod 2 multiplicative. But so you have little more for d equals 1, but much more for bigger values of d. And one can at least conjecturally understand how much more to some extent. Now, why would an algebraic geometer look at such quantities? It's because there is another formula for the same numbers which makes sense. This does not make sense for an algebraic geometer. So it's an infinite sum. Algebraic geometry works with finite quantities, if possible. So there is another expression which I will first give it for zeta S1 of SD. So you do the following. I will first write a series of differential form. dz over z, dz over z, a number of times. Then dz over 1 minus z, and all of them, there would be S1 of them. Then I do the same thing with S2, and so on. So I obtain like that a sequence of summation of Si, the weight differential form, which I will call omega I. So I equals 1 to the weight. And when one has this series of differential form, one does the same thing that what we did for the iterated sum. One starts with the least one. One considers its integral from 0 to t. This is some function of t, or maybe of z, I don't know how I would call it. At least well defined when absolute value is z is smaller than 1, or you have to, here at the end, I recall you have a dz 1 minus z, so you have to be a little careful at the pole at 1. So you take this function, you multiply it by the previous differential form, which is either dz over z or a dz over 1 minus z. And again, these new things you integrate up to 0 to variable limit. You get a new function of z, and you repeat the process until the end. At the end, you integrate from 0 to 1. So this is what I was trying to explain for iterated sum. You do the same for iterated integral. And if you want to write it just at one go, you say that it's the integral for 1 bigger than t1, bigger than t2, bigger than t the weight, bigger than 0. So you have those inequality, and you are real between 0 and 1 of omega 1, omega 2, omega the weight. Now, yes, and so the claim is that if you do this, you obtain zeta of S1 SD, and the proof is completely trivial if you allow yourself to expand dz over 1 minus z by the geometric theory. So you first consider dz 1 minus z. You write it is summation n at least equal to 1 zn, sorry, 0, dz over, sorry, no. No. Either IF at least equal to 0 Zn, or at least equal to 1 with dz over z, which I prefer. Now, if you multiply by, so yes, and now if you yes, now you can integrate term by term, multiply by dz over z, integrate term by term, and so on, and successively you see appearing the function summation zn, summation zn over n, summation zn over, yes, n square, and so on. Each time you multiply by dz over z and integrate, and then when you multiply by dz over 1 minus z and integrate, you will start seeing appearing some for n1 bigger some n2, and so on. So if you do this up to the end, what you obtain is summation zn1 over n1 s1 and d sd, which you have to evaluate at z equals 1. So this is one of the instances with this integral up to z of those generalization of multi-zeta value when one free this one and take all the previous one equals to 1. And clearly, if you put here this less d equals to 1, you obtain the multi-zeta value. Now, when one has, so what one has obtained as expression now is, I would prefer to think in this form. So what you have, what you integrate is some algebraic differential form, this product of dz over z and dz over 1 minus z in different variable. Now, the locus you integrate on is some train. For d equals 2, it's this train, t1 and t2 in the interval 0, 1, and t1 bigger than t2. And now you will observe that this train has its boundary on algebraic subvariety of C2, in fact on lines. So you have the form of this integral, it's that an integral of algebraic differential form on some chain on some algebraic variety with the boundary of the chain contained in some given subvariety. Now, the situation is not completely clean in the sense that the form one integrates as some locus of pole, and this locus of pole touch the boundary of the chains we want to integrate. But one should think to that as just a technicality and somewhat forget about it. Of course, it's what is responsible for the fact that zeta of 1 does not make sense, or that one has to regularize it in some way. For higher S1, the integral one has to take will be a convergent integral, but one can do things as a kind of summation process, even a convergent integral. So it's not as it is completely in the form of some period in the sense of algebraic geometry. One would have to fiddle a little with it, but I think it's safe to view this as a technical problem and to forget about it. So if one does, then one has a general format that one has some cohomology group or relative cohomology group, like here, of which one has the Durham realization, and this is an element of this Durham realization. One has the dual homology group. So here, the exponent here is the weight W, the sum of the SI, the number of differential forms involved. There is dually some corresponding homology group, which one considers topologically, looking at integral chains. One has a pairing between the two, given by the integral. And so this is a period, what is obtained by pairing an object of the Durham cohomology. So nice form, everything described in terms of rational numbers. And Betty, some integral chain, so two different notions of integrality. And within this, one does the integral pairing, one obtains periods, and those multi-zeta are periods. Now, how does it help? So here I would like to explain Grothendieck philosophy for periods. So this will be applied to those multi-zeta value, but not immediately. So if anything kind of cohomology you want to consider, like relative cohomology of an algebraic variety and a subvariety, and as a whole you have various ways of looking at it. You have the Durham point of view, where you compute with differential form, say with rational coefficient, like here, if one starts with variety defined over Q. One has the same in Betty realization, when one uses the complex variety and one does ordinary cohomology on this complex variety, and then one has a comparison isomorphism between the two. So if one starts with variety over Q, one has Q rational vector space and an isomorphism between their complexification. And so this is comparison isomorphism, telling that one has over the complex two ways of computing the cohomology, each way giving a rational structure. And now, if I use some rational base of h the Ham, some rational base of hb, those periods are coefficients of this map as a matrix in those bases. I prefer to tell it like this than by using the dual, as I was doing there. So this is one has this notion of periods in this case, and tell roughly the Grothendieck philosophy is that any algebraic relation between periods, so say polynomial equation with rational coefficient, would have a geometric understanding. So this has to be said little, yes, I have to precise, this is a number of ways. First, I was first telling the case of variety over Q. One can also consider variety over a number field. Then the Ham cohomology group are vector space over K, so here one should tensor over K. And to speak of Bethe-realization, one has to fix an embedding of this field into the complex number, which I have to use. And this now is the Bethe cohomology group of the variety over C obtained using this particular complex embedding. And the statement is the same. Now one has some matrix whose entries are in K, with, one has some matrix, entries are complicated number, and one would tell that all algebraic relations with K coefficient would have some geometric, one should have a geometric understanding for them. The statement, if one take all varieties are essentially equivalent, if one sticks with variety over Q, or if one allow also to be over K. Now, how to state it a little more precisely. On some cohomology group, there are some structures coming from geometry. For instance, a structure belonging to multilinear algebra. For instance, we have some cup product map, some duality pairing, some functoriality map between various cohomology groups. All of this has a geometric origin, and because it has a geometric origin, it makes sense in all cohomology theory you may want to use, and it will be compatible with the comparison isomorphism. So you have this cohomology group you want to consider, and let us consider all structure coming from geometry. Now, if I look at, say, first h the Ham, I can look at the group V the Ham of automorphism of this vector space given with all those structures. And I can do the same for Bethe or sigma realization. I get some group V. So, for instance, if the structure you have on H is alternative, let it be a symmetric form, this would, and we have no other structure, this would be an orthogonal group. Now, if you extend scalar, let it be with variety over Q, not to have technicalities, and it's the main case for us anyway. So you have those two vector spaces, they have some structure. Over the complex, they become isomorphic. Now you can also, before going to the complex number, looking at the scheme of all isomorphism of one with respect to the other. This is a variety which may have no point over Q, but still you can look at the variety of isomorphism from here to if you have two vector space with a quadratic form of the same dimension, you can look at the space of isomorphism between the two. It's a torsor under the orthogonal group. So it makes good sense.
Sorry, G dram was the automorphism of H dram.
G dram is automorphism of H dram and GB automorphism of HB. And in between the two, we have isomorphism of H dram with HB. And this is a torsor under G dram and a torsor under GB on two different sides. And the comparison isomorphism is a complex point of this variety. And now, expressed like that, Grothendieck's philosophy is that this point would be a generic point. And that if you look at all algebraic equations, if you look at the Zariski closure over Q of this point, the smallest algebraic variety over Q, which over C contains this point, you cannot do better than P itself. So no, that's a nice philosophy. It's completely hopeless in general. It's very hard transcendent question if you want to prove things like that. But at least it's a guiding principle. It tells you that there would be some reasonable identities, those which have had to exist between periods, and that if you look at the variety defined by those identities, it would be such a torsor under this group of automorphism for either G dram or GB, as you may want to consider it. And note, yes? It's not clear. He was thinking to pure motive, I think. So I don't think Grothendieck really considered mixed object. And here, of course, it's basically mixed object which we are interested in. So maybe I would say inspired by a conjecture in the pure case. It's an amusing exercise to check that if you consider K finite extension of Q and you consider spec K, then you have H dram. You view it as an algebraic variety over Q. You have H dram, you have H betty, and you can check that it's true in that case.
What was the conjecture?
That this comparison isomorphism, which is a complex point of P, is a generic point. That it's a Zariski closure over Q is the full thing. And if I had an algebraic variety over a number field K, I would have again, now over K, I would have G dram and such a torsor and a point in it, and again one would like that this point be generic over K this time, that the smallest K variety containing it is the whole of P. So it's at least a guide of what one can hope if one is optimistic. But for me, the way it comes is more as a challenge that whenever you know some algebraic identity between periods, you want to put in this form and to find a geometric structure which explains why it is true. And in the case of multi-zeta, this is really not obvious. Let me explain one of some simple identities about multi-zeta to see what we are up to. So I will give the first theorem which made Euler famous. And I prefer to write it like this, because 2 pi I, that's clearly something which is a period. It's the integral of something around 0 in C multiplicative of dz over z. So that's prototypical period. And now for this zeta of 2, we have this kind of expression telling it is a period also. So we have here something to explain why those two periods have this relation between them. Now one can look at the proof Euler gave, which is a beautiful proof. Euler considered the function sine of x and said that one should consider it as a polynomial of infinite degree, and so one knows it if one knows the derivative at 0 and all the zeros. So this leads to the formula x product 1 minus x over n pi, where n from minus infinity to infinity, but omitting 0. That's why I had this. So one has to be slightly careful. One should group together the term for n and minus n. Here one sees well the zeros, but one has to do this for convergence. So I had rather so one has this identity, and also you know the Taylor expansion of sine, and you compare both. So here, if you look at the coefficient of x cubed, you have one term for each x square coming up. So here, from coefficient of x cubed, here you find summation 1 over n square pi square. So that's zeta of 2 times minus 1 over pi square. And here you find minus 1 over 6. So you compare both and you obtain this identity. So that's the first proof of Euler. Then even for him this was a little far-fetched, but he convinced himself it has to be correct, because he also checked that both sides were agreeing up to 10 decimal or something like that. So this was enough to give confidence that the argument was really sound. Yes, as long as I am at it, I can tell that from this one can get other identities. First, as earlier I did also, if you take logarithmic derivative on both sides, then you will see appearing altered zeta of 2s, and that gives the proof of the expression of zeta of 2s as pi to the power 2s times some explicit rational number. You can also keep it like this and look at what you get as coefficient from some x to n if you expand the product. So you will need to use, so if I use the x power 2s of x here, it means I will have to use s factors, and the contribution of, if I pick those s factors, I will have the corresponding product of 1 over n square. So I leave it to you as an exercise to check that doing this one obtain multi-zeta 2 to 2 s time to be equal to pi 2s divided by 2s plus 1 factorial. So that's another identity coming from this expansion. Yes, I was speaking of Euler, so he really gave an honest proof of this identity later, and then things worked well. And also now we have a good theory of such expansion of holomorphic function in terms of those zeros. Sines grow a little fast, but it has some symmetry from x to minus x, which make it better. And then the theory applies just that it is to prove this expansion. Okay, so the situation is you have a lot of tricks to obtain identities between such multi-zeta value. I will give one other which is interesting. Consider a product zeta p, zeta q. So that's summation 1 over np times summation 1 over mq. So you sum over integers n and m. Now break this sum into 3. N bigger than m and m bigger than n, and both being equal. So what you obtain is zeta of pq plus zeta of qp plus zeta of p plus q. So we have various manipulations either of theory or of analytic function which give identity, and the proof of those identity does not suggest anything or how to find what geometry is behind it. So it's quite remarkable that so far any identity one could prove among multi-zeta or in general among periods can also so far be given some geometric understanding. It's really a kind of reckless conjecture because there are so many ways to prove identities, so it's quite remarkable that it holds true at least so far. Yes, there is an additional twist in this story of multi-zeta, is that in this expression, yes?
The precise statement that you made just now, is it that all the multi-zeta identities so far are consistent with the
Yes.
statement?
Yes.
What's actually broken in conjecture when you have identities between periods and two different
Oh, you consider either the disjoint sum of the two varieties or their product, and then they are on the same variety. In fact, you could put more and more varieties together. Even if you want to look at one variety, you put some other on the side, and it gives some bigger group acting on the product of the HI, and you project to the cohomology group you are interested in. So relation with other group or existence of other group with bilinear relation of linear algebra count as a structure here also. Like already when I thought this, I wanted to tell something about zeta of 2, but I introduced another variety which was the multiplicative group and its first cohomology group, and then I had indeed two varieties to play with. Yes, two things. The first one that's a question of terminology. This group I introduced with some vagueness, speaking of all structure coming from geometry, is also what one calls the motivic Galois group. That's just terminology. One thing to observe is it is not really one group. For each cohomology theory, it has an incarnation where it acts on the corresponding space. So from that point of view, is in itself a motivic object, something which has an incarnation in each cohomology theory. And to the extent that one has some formalism of motive, and in fact one has, in this case of multi-zeta, one can speak of mixed-state motive, one can look at their category, and then what one can consider is all mixed-state motive and the relation between them mapped from tensor product of them to another. And then this group becomes the group of the corresponding Daniken category. And this explains perhaps terminology motivic Galois group. But for me, this is a more intuitive explanation of what it is. Yes, but what one has in addition in the multi-zeta case is that one has tools to prove existence of structure of some type without exhibiting them. Essentially, in this case, one has some a priori control on what the motivic Galois group is if one look at all mixed-state motifs, say with some property like unramified over spec Z. And so what it means, if you have some particular motif, you put it among all mixed-state motifs, you have some group of which you know something about, and then it tells you something about what this group is for this particular mixed-state motif. And that's the way one has to obtain some a priori upper bound on the number of independent multi-zeta values, say of some weight and up to some depth. So it is this, from this philosophy, starting from the picture of motive, but it's kind of cheating, is that one proves existence of some structure, one does not exhibit them, and we really don't know in general, no, we don't know it in any case, we cannot prove that the structure one can make explicit give all the structure which in fact exist and which explain what truly should be the algebraic relation between multi-zeta. So now I will essentially quit the multi-zeta. I wonder if that's not a good time to make a break. It's not yet 1 hour, but maybe if there are questions also, because now I will have to speak of things like group made unipotent and so on. So I suggest a break now. I don't know for how long, and maybe questions also.
Are these groups connected?
In the case we are here, yes. In general, no. So conjecturally, if you look at many varieties over Q, that will be all, so it's a very big group. Then you have this motivic Galois group, call it G, and let me use the Betti realization, and then it will map to Galois group of Q bar over Q, where this corresponds to only to the cohomology of finite scheme over spec Q. And the period conjecture would imply that the kernel is connected. So this is the disconnected part, and then you are left with the connected part. There are a number of conjectures implying that the kernel is connected. The odd conjecture would imply it also, for instance. But the period conjecture does it as well. That's very big. So for instance, if in practice it's too big an object, so you would like rather to take a few motifs, and then you wonder what the corresponding G is. And if you take just one elliptic curve with no complex multiplication over Q, you want GL2. There would be no other structure. But if the curve has complex multiplication, then you will get something dihedral, K multiplicative and complex conjugation. There it would be disconnected if you work over Q. If you work over K, then it will just be the multiplicative group of the quadratic imaginary field. Now, also things depend of what category of motif you work with, what counts as something coming from geometry. For instance, if you consider abelian varieties, there is one definition where only algebraic circle on product of algebraic variety, on product of abelian variety are what can be used to define structure. No, you can be more reckless and allow also odd circles, and using the fact that it's an often independent of the complex embedding of the field you are in. And so two would give rise to different groups. And in the case, for instance, of abelian variety, absolute odd circles are good enough to give information between periods. As if the odd conjecture were true, the identities among periods are true. But you see, if you take a number of elliptic curves, usually you expect one GL2 for each of them, except if two are isogynous or things like that. So it's a very big group, but if you have one object, it still has some reasonable size. It's being a subgroup of some product of linear group for the motif you want to consider.
Incidentally, a kind of equivalent. If you take one elliptic curve, then the GL2 should be a subgroup of the other quotient.
Sorry? So for an elliptic curve,
Compared to a few elliptic curves.
A quotient. So if you have many ever, yes. It's a group scheme, I would say. Like this is a profinite group, it's also a somewhat big group scheme. Yes. Yes. But there are affine algebraic groups, so.
In this connectedness conjecture, your G is for all motifs, right?
Or many of them. I need enough to map onto this Galois group to have this thing defined. So I need some system of motifs containing all spec K for K finite extension of Q. And if I limit myself to those, the connectedness condition here is a consequence of the one. If you take a few motifs, or if you take all, you will have map like this. And so connectedness for all implies connectedness for a few. This connectedness is something which is not clear at all. And let me give one example of motif for which presumably one can prove enough, but it's not clear. So take some variety over Q, which I take to be of even dimension. Now I can look at the middle dimensional cohomology group, the projective non-singular. I take the h to n, I twist it twice by n, and now here I have a quadratic symmetric bilinear form, which is given by a product. And I can also consider the exterior maximal power of this h to n. And here I obtain some motif, which I will call M, and the symmetric form gives me an isomorphism of this tensor square with the unit motif, the H0 of a point. So I am over Q everywhere. Now the connectedness convector in this case tells that yes, even dimension 2n.
Sorry, what is M?
So that's M is this maximal exterior power of the middle dimensional cohomology. And because you have a symmetric bilinear form here, we have one here also. And this means that the tensor square of this object is trivialized. And it's all true for all realization. And now the connectedness convector in this case tells that the only way to do this is to have essentially a spectrum of a quadratic extension. Rather removing from this H0 of Q. This is something of, but this tells something which is not clear at all. Therefore, each L-adic cohomology, you will have a character of order 2 of Galois Q bar over Q, and what the claim is that this character is independent of L, the L-adic cohomology you use. And also it tells that if you look at the Durham story and at the period, you will see something like square root of D as a period, that all those things would come together. I would expect that in this case one can prove it, but it's not at all an obvious statement.
Any question? No, we'll take half an hour break, I guess, for tea. There's tea upstairs or somewhere. And then we'll restart at 4 o'clock.